Hello everyone. Today we are going to see about Poisson equations. Now let us see the what to do in Poisson equations. Like this is outline or you call agenda anything. In first we will see introduction, second applications, real world cases, working techniques, finite difference method steps, and last we can see the conclusion. Let us see about introduction. Poisson equations is the second order partial differential equations that appears in various physical and engineering problems given by, like it is also mentioned in the formula type and mathematical condition as delta square into phi equal to f of x comma y comma z, where the delta square is the Laplacian operator and phi is termed as scalar field, and f of x comma y comma z is the source term or the distribution of a physical quantity. Let us see deep about the Poisson equations. As I also mentioned, second order partial or real partial differential equations that arises in various fields of science and engineering. It is named after the French mathematician and physicist Simon Denis Poisson, who made significant contributions to mathematical physics. The general form of Poisson's equation in three dimensions, like it is also 3D. Let us the terms various. It represents a mathematical condition of Poisson equations. In first we see delta square is the Laplacian operator, which is divergence of the gradient of a scalar function phi. Phi is the scalar field that we want to determine which could represent physical quantities such as temperature, electric potential, or fluid pressure, depending on the application. F of x comma y comma z is also known as source term or function that represents the distribution of sources or skins of a scalar field in the region of interest. Let us see about the procedure of Poisson's equation. Poisson's equation is a mathematical tool used to describe the distribution of a scalar field phi in a given region. The equation is derived from fundamental principles in mathematics and physics, and it finds numerous applications in engineering as well as scientific fields. That is the various. First one is deriving Poisson's equation. Second, numerical solution using finite difference method, visualization and analysis, application specific analysis. Like we can see the first deriving Poisson's equation. Deriving Poisson equation. Poisson's equation can be derived from Gauss law, which relates the electrical flux passing through a closed surface to the charge enclosed by that surface. By introducing the concept of electrical potential phi as a scalar field, we can rewrite Gauss laws as delta into E equal to rho by epsilon naught, where delta into E is the divergence of the electric field E, rho is the charge density at a point in space, and epsilon naught is the vacuum permittivity. Let us see the second one, numerical solution using finite difference method. The analytical solution of the Poisson's equation is often challenging or impossible to find for complex geometrics or non-uniform source terms. In such cases, we turn to numerical methods, and one commonly used approach is the finite difference method. Let us see what is the finite difference method. Finite difference method includes various steps or method steps that are discretization of Laplacian, building the linear system, incorporating boundary conditions. Solving the linear system also it is the last and important step for the finite difference method steps. Let us see the one by one. First one, A, discretization. The continuous domain is divided into a grid of discrete points with grid spacing delta x and delta y, like it is mentioned in the two-dimensional problems. But in various, like I also mentioned in the previous slide, that it is a Poisson's equation is determined in a three-dimensional. But in this discretization, specifically mentioned for two-dimensional problems. Let us see the discretization of Laplacian. The Laplacian operator delta square phi is approximated using finite difference formulas. The most major important is the standard 5-point formula is commonly used for its simplicity and accuracy. Building the linear system, applying the finite difference approximation to the entire domain results in a system of linear equations. Each equation relates the value of phi at a grid point to its neighboring points. D. Incorporating boundary conditions. Boundary conditions are essential to uniquely determine the solution. These conditions set the values of phi on the domain boundaries. Different types of boundary conditions are used, such as Dirichlet, Newman, or mixed conditions. Last, we can see the solving the linear system. The system of linear equations is solved using numerical methods like iterative solvers, as I mentioned, Jacobi, Gauss-Seidel, or more advanced techniques conjugate gradient, uh, multigrid. The solution process iteratively updates the values of phi until convergence is achieved. Let us see the virtualization and analysis. Once the numerical solution is obtained, engineers as well as scientists, because not all engineers have to be scientists, that is not perfect, visualize the scalar field phi using the various techniques such as pilots, contour plots, surface plots, or color maps. These visualizations help in understanding the behavior of the field and identifying the region of interest, such as extreme values of gradients. Next, last application specific analysis. The numerical solution of Poisson's equation allows engineer scientists to analyze specific engineering problems. For instance, in heat conduction problems, the temperature distribution in a heat skin can be analyzed to optimize its design better cooling efficiency. In semiconductor devices, the electric potential and charge distributions can be studied to improve device performance. In summary, Poisson's equation is a powerful mathematical tool used to model and solve a wide range of engineering and scientific problems, as a skin problem, image processing, like various companies like big companies Samsung and Sony. It is used in image processing to correct the pixels. Its numerical solution through the finite difference method enables engineering to gain valuable insights and make informed decisions in various real-world applications. Let us see the about engineering applications of Poisson's equation. First one is electrostatics and capacitance. In electrical engineering, Poisson's equation is used to model the electric potential distribution in conductors, insulators, and etc. It helps in calculating capacitance values and designing electrical systems. Second one is second one is heat conduction. Poisson's equation plays a crucial role in modeling steady-state heat conduction problems. It helps in determining temperature distributions in conductive materials and is essential for designing efficient cooling systems. Like also mentioned semiconductor devices, fluid mechanics. As I mentioned, the big companies are used in this Poisson's equation as a role model because their camera quality can improve by using this in image processing sensors. Like various sensors on XM890, etc. What is the real world engineering cases? Like ESP, heat sink design, and semiconductor device simulation, boundary value problems, medical imaging, electrical field simulation. Let us see the first ESP. ESPs are widely used in industries to remove particular matter from flue gases. Heat skin design in electronics cooling applications. Engineers use Poisson's equation to analyze the temperature distribution in a heat skin. The analysis helps in optimizing the heat skin shape and fin arrangement to heat effectively. The real-world cases demonstrate the significance of Poisson's equation in engineering and its wide-ranging applications across different industries and by fields. Summary: we can see the word applications, analytical and numerical methods, boundary conditions, engineering applications in the previous slides. Now, conclusion: Poisson's equation is a fundamental partial differential, as I mentioned in the first slide only, that plays a central role in modeling various physical phenomena. Its solutions are essential understanding and predicting the behavior of scalar fields in a numerous real-world applications. Thank you.